Hello everybody, my name is Sahil Trivedi and this is my Lab 6 on magnetic molasses for Physics 2212. So, jumping straight into it, in the introduction, you see the purpose of this experiment was done to analyze how a falling bar magnet would interact with a surrounding metal tube and account for differences compared to another model, which is the computational model. The key concepts here are the Biot-Savart law and Faraday's law. This is mainly important for knowing where the current points and the induced current and how the induced current can counteract the direction of gravity, which will either speed up or slow down the descent of the tube. And this lab really focuses heavily on induced current, where it's located, and the effects it can have on the falling system. Looking at the setup and initial conditions, you can see that you have the bar magnet, the stopwatch, this aluminum tube. For our results, all we got was that the experimental time was 1.21 seconds and the computational time was 0.94 seconds, which is a wide range of differences, which we'll discuss what these are attributable to in the rest of the lab. And on the right side, you can see basically what the tube should look like. Looking at our computational model, it basically just starts off with defining a bunch of our variables like the resistivity, our K value, as well as gravity. And then we're attempting to make a plot here so we can directly see, how does the falling change over time. Taking a look at the tube, here are the dimensions all laid out. And then on the right side, you can see the mass and the magnitude for our magnetic dipole moment. And then the bar and the bar mu basically are just telling us what is the position and axis vector. So here's the results. You can see in this graph how, we start at 0 and then the velocity takes this big sort of dip at the beginning over time and then flatlines until reaching a faster velocity at the very end, which is around when it leaves the tube. And you can see the kind of steady state in the middle here and then the quick acceleration down at the very beginning as it's falling through the tube and the flux is increasing. So to mention again, the experimental time was 1.21 seconds, while the computational was 0.94. In these observed similarities and differences, the bar magnet is basically a dipole for the Biot-Savart law, and there is negligible air resistance. So, taking a look at all this, we can see that there is a number of errors that would lead us to believe that the experiment time was increased. So, for our sources of error, we think that there's forces related to external electronic and magnetic devices that could have been a problem. Obviously, you have the magnetic fields outside from any sort of metallic object moving. You have the friction down the tube, which is a big thing we think, as well as the air resistance, especially for an object that's quite large and slowing in descent. We think that these could add up and increase the time. And then just timing problems of, clicking the start and stop. It's not as perfect as the computational model, which was all coded in. Having a look at our discussion, for number 1, we have what is the resistivity of the conductor, what is the resistivity if the conductor were reduced as close as possible as 0, and how the dynamics of the falling magnet change. Due to Ohm's law, if the resistance was reduced close to 0, the induced current would be much greater because there's nothing limiting how high the induced current can reach, and this would cause it to fall extremely slowly. Because the induced would counteract gravity even more by magnitude, and it would slow its descent. Taking a look at what if holes or slots were cut into the tube, and how would this affect the ring currents in your model. The induced current in the aluminum tube would be less, and the magnet would fall far quicker. This is primarily due to the fact that the induced current in the aluminum tube is dependent on how fluid it can go throughout the entire magnet, and since there is less surface area to go around on the outside of the magnet, there's less induced current going to be generated that's going to go against the walls of that aluminum tube, and then you would see its descent go much quicker. That's why if you had extremely fragmented pieces of the magnet all cut up, the moments wouldn't be as much, the magnitude wouldn't be as much, and then they would all kind of just fall like normal, and maybe the induced current could be negligible compared to the force of gravity. So that is the end of my presentation for magnetic molasses. Thank you for watching for Physics 2212. Thank you.